Hello and welcome to the EMC Live Roundtable, Analog RFI Immunity Challenges. My name is Belinda Stashukevich and I'm the editor of Interference Technology, the creator of EMC Live. EMC Live is a brand new online 3-day event hosted by Interference Technology. Featuring practical information and topics, this event will include roundtables, events, and webinars and videos on everything EMC related, and there's no cost to attend. Join us for our other webinars and roundtables this week. This roundtable today is moderated by Doug Smith. Doug's an EMC engineer and owner of DC Smith Consultants. He runs a high-frequency measurements webpage with monthly technical tidbit articles and HF News email newsletter. Specializes in design and troubleshooting tips. Panelists on this roundtable include Tom Braxton, project engineer at Shure Incorporated, and Mike Schnecker, electrical engineer at Rohde & Schwarz. This roundtable will be interactive. You will be able to ask questions, and we encourage you to participate. Take a look at your GoToWebinar navigation pane, the box on the right-hand corner of your screen. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or report an issue, click the hand icon. We'll discuss the topic for 30 minutes, and now Doug will kick off the roundtable.
Okay, looks like we have 62 here. Belinda, will you at some point give me control over, so I could show my screen if necessary?
Oh, sure, we can do that.
Okay, let's do that now.
All right.
And then show my screen. Okay, so with our other panelists here, let's, wait a minute here. There we go. We're going to have a quick 1-minute introduction of each, maybe 2 minutes, and I'll pose a question to each of you that you can sort of put in there. The question is going to be, have you personally experienced problems with RF interference with analog op-amps? So let's start off with you, Mike.
Yeah, that's kind of an interesting question. I guess not specifically that I recognize, but I'm sure I have.
Okay, and just a word about your background.
So I spend most of my time in the test and measurement industry. So I work with a number of companies, working with both RF products at Tektronix and also with oscilloscopes at various companies, including Tektronix and Rohde & Schwarz and LaCroix. So about 25 years or so in the industry, and just a lot of different disciplines.
Okay. Tom, how about you in terms of experience problems with RF problems with op-amps and a little bit about your background?
Yeah, op-amps at the individual level, I've seen very few of those, but op-amps as part of a large-scale integration type device they have. And yeah, certainly we've seen, in my experience anyway, I've seen plenty of RFI, EMI interference going on with analog circuitry. It's natural occurrence. And so yeah, and doing that kind of work, you see that all the time. In my own case, yeah, I've been working a little over 30 years in various forms of EMC work. We're currently at Shure Incorporated as an engineer here in the compliance group. And for many years before that, I was an engineer at AT&T Bell Labs and later Lucent. And I did some consulting work as well.
Okay.
So that's my background.
Okay, and I think Belinda did a fairly good job of my background, so I don't need to go into it. Except that although I do EMC, I also do ESD, and maybe a third of my work has nothing to do with either just general analog and digital design. And I had actually 2 more questions I'm going to quickly ask because I want to get to people's questions, not ours. But one of them is, have you worked on these problems? And I've been working on them for about 30 years now. The first time it happened was an operational amplifier was reacting to logic noise on the next board over in a shelf of boards. It was amazing. You could slide a copper sheet in between them ungrounded, and it would make the op-amp quiet. So that led to some interesting investigations, and since then I've experienced one of the latest ones was a position sensor on an automotive application that went to full position in the presence of RF signals roughly in the cell phone band. If that's your throttle position sensor, that's not good. So lots of problems like that. So have any of the other, Mike or Tom, have you, judging from your discussion, I don't think you've actually worked on those kind of problems, have you? Is that true? Mike?
Is this Mike or Tom?
Either one.
Yeah, go ahead, Mike.
Go ahead. Yeah, not directly. I mean, one of the things that we have done, techniques that we've utilized is the issue with the position sensor problem, for example. One of the things that we've done is use near field probes to look very close to the circuit and see. For the near field, you can't talk about signal strength, but you can talk about specific frequencies, and you can sort of identify the coupling mechanism, which is usually the way to get to the root of the problem, and work backwards from the coupling. So say you've got maybe a poorly grounded cable going into a box, and that cable is coupling to a clock inside that digital circuit. Well, that thing becomes an antenna.
Okay.
And so that was the trick that we use a lot to do that.
By the way, you can get a feeling for instance, with a 1-inch square wire loop. Fed about a watt, that gives you voltages and currents that are comparable to a 100 volt per meter field right against the circuit. And you can measure those and you can see those. But the round EMC loops don't work for that purpose because you don't know what the coupling is very well because they're round. So Tom, do you have anything to add to that?
Yeah, actually, the phenomenon is really it's the same mechanism, whether or not it's a true op-amp with differential inputs or a regular analog circuit with a single input. But the point remains, if there's RF interference and it finds its way into a circuit, and it will, there's going to be rectification somewhere at a PN junction or a solder joint or somewhere.
Right.
And when that happens, interference happens, and certainly, we'll chase many of those down.
And the interesting thing is that a voice frequency op-amp with, say, a 1 megahertz gain bandwidth product has no trouble responding to a 2 gigahertz signal. All it takes is a junction that's good enough, doesn't have to be a good one, and it shows up as an offset, and then the modulation on the RF shows up as modulation on the DC offset, sort of like a crystal radio for those of you old enough to know what that is. One other quick question, and then we're going to get on to other people's questions. What are your courses of action for fixing these kind of problems? In other words, what have you done that fixed the problem?
Well, I can, in my own experience, this is Tom, it runs the gamut, of course. First, you try to isolate what the source of the problem is, and typically it's some external source.
No, I think more of what did you do that fixed the problem?
To fix the problem, yeah.
It's supposed to find it.
Well, right. And once you identify, after it's been identified, then fixing the problem at the circuit level usually encompasses some form of decoupling or current limiting in the signal path. Okay. And especially with op-amps, as you say, it can mess up the offset if there's interference in there. So if there's decoupling, or if you have the luxury of choosing a device that has a high rejection ratio, that's the way to go too.
Except they usually don't. The power supply rejection, say, or common mode rejection, is generally only characterized at low frequencies or maybe up to the unity gain bandwidth of the thing. Right. Not at 2 gigahertz, unfortunately. I wish they would, because then we could pick these things out of data sheet. Mike, how about you?
So I think most of the solutions that I've run across have been involving just improving grounding and making sure that the ground plane on the board doesn't become an antenna, because the key thing is trying to reduce the gain going into the circuit. And,
okay. So the things that I've found are, even though it may be a low frequency instrumentation amplifier, you have to do one of two things. You either have to actually, you may have to lay out parts of the circuit as though they were 2 gigahertz digital circuit. I mean, really close spacings, pay attention, we're grounded. The loops turn out to be very important, which they may not have been at 101 kilohertz, but the 2 gigahertz allows the loops in the circuit to feed the RF into the op-amp, and then you end up with a problem. And so layout is much more critical than you would think for the frequency. The other thing is, I've found if you put a capacitor, and let's see, I think I have it here. Here it is. Let me make it bigger so you can see. It's just a hand-drawn thing, one of the pictures from my website. If I put a capacitor, plus to minus input, on an op-amp, you can kill the RF. And there's two things about the capacitor. Very small. For feedback resistors on the order of tens of K, that might be 47 picofarads. But you shouldn't put it there without doing a simulation or a measurement first, because it does lower the phase and gain margin of the amplifier. and can cause problems. But generally 47 picohertz is safe for a few tens of Ks kind of feedback resistors. If you have much higher feedback resistors, and many circuits do these days, then the capacitance would be correspondingly smaller. The other thing to note on this diagram is the distance out to the bypass capacitors is very important. They should be right next to it. Even though you're running at very low frequencies maybe, you're trying to prevent the loops that would get the 2 gigahertz into the op amp. So let's, how about questions from the audience here? I'm looking in the pane here, waiting for someone to type something.
We don't have too many coming in yet. We want to encourage the audience to send some in. We did have a comment from an attendee who said that they've worked with analog op amps, and in their case, they've been able to use their feedback network to implement an appropriate narrow band filter to pass the appropriate signal and block the rest. Do you have any thoughts on that?
That would work up to a point, but when you're talking about 2 gigahertz, I bet that feedback network's not characterized at 2 gigahertz, and the op amp doesn't even act like an op amp at 2 gigahertz. So I'm not sure that you can handle it by feedback for that. And 2 gigahertz is important because that's near the cell phone upper band and it's near the wireless band, both of which are big things these days, and your product might be right next to one of these gadgets, even though they're not powerful transmitters. The distances can be very small, and so it gets into these things. But I think the feedback network probably would work up to the point where the operational amplifier is characterized too. By the way, another way of fixing this, this just happened with a customer of mine. They had a problem. It was this position sensor indicating full position with cell phone kind of frequencies, upper band. They don't characterize op amps for these kind of problems, at least many companies don't, but this particular company had 4 possible op amps suppliers they could use. 2 of them were really bad, one of them was pretty good, and the other one was so good it made it pass without doing anything, just by selecting the manufacturer. So, but if you do that, you've got to either let the manufacturer have you make sure they let you know of any changes to their process, or do a little test every once. Build up a test jig that's sort of like your own circuit. Maybe on a nice right over a ground plane to keep RF conditions constant, and then feed in a controlled amount of RF and see how sensitive it is, directly connections, like through an SMA connector or something, and then characterize it, and then once in a while check incoming and make sure that they haven't changed a lot.
Okay. We have a few more questions coming in, so Doug, you or any of the other panelists?
I don't see questions coming in on my screen. Why don't I?
I'm not sure you guys have a different screen than we do, but we can send them to you if you'd like.
There's a place for me to type an answer, and there's a question in an asker field, but I don't see any questions showing up.
Okay, we're going to send.
You just read the question. That would work.
Okay, you read the question.
Yeah. Okay. We have a question that asks, although a 360-degree metal shield is probably the most effective shielding technique to minimize RFI immunity issues, it's not always feasible for a product. Ferrite-filled plastics have been shown to be very non-effective as an alternative. Any ideas from the panelists on shielding techniques short of traditional metal shields?
We'll start off with Mike, and then Tom, and then I'll follow.
I wouldn't consider myself an expert on shielding, but I think that any shield is going to be a problem because you've got to get the signals in and out of it, and it's not going to be complete, right? It's not going to be perfect. So, I mean, I guess like the techniques that you're talking about here about putting decoupling caps is probably one of the best things you can do. So, rather than trying to brute force shield it, just try to handle it locally.
Tom?
Yeah, and I'd say, again, the punchline to every question about EMC, the issue is it depends, but it does, because if, in the case of an op amp, if there's a specific area on a circuit board that is sensitive to some interference that you're aware of, one attempt I've seen this done successfully is to get a specific board level shield around that device. Now that obviously only works if it's a 360 shield around the device and if the ground connection there on the board is clean. That is, not only is a good series of connections around that shield, but rather is the ground itself low noise and is it low impedance to ground. If that works, or if those things are all true, then the shielding can be effective.
Okay, the one thing to be careful on shielding, metal cans are nice. If you'd have to open up on the top of the circuit board, expose the underlying ground layer, solder it down to that, and then every lead coming in and out would have to be bypassed. Since we're probably talking about op amps that are relatively low frequency, bypassing for 2 gigahertz signals is probably not that hard to do. Then you do have a thing. Of course, that's very expensive, and sometimes I run into customers who say, we got to fix the pollen, but you can't spend any money or change the design. I've had that more times than I can remember.
Yeah. Standard procedure.
Yes. But if you select something other than a metal can, you cannot trust any of the published shielding effectiveness numbers because they're all far field, and we may be talking about a near field possibility. For instance, the op amp may be picking up RF from the next board over or something on the same board. And none of the shielding, all the shielding numbers are published or far field. And for close field, they're way off. They don't even hold. You have to do your own tests. If you go to my website, emcesd.com, and look for the word shielding, you'll see a test that you could do on your own to evaluate shields for that kind of source. But by the way, there's about 250 other articles that are talking about everything you can think of. But I love to do experiments and write up things. But anyway, generally shielding of op amps is not something I've seen people do, and I haven't done myself. I suppose if I have worked on op-amp circuits, this was for a Mars mission, that used gig-ohm resistors, and their frequencies were like an audio band, but when you talk about gig-ohm resistors, boy, parasitic capacitance to everything, including a shield, affects the circuit response at baseband, and that's an interesting problem. But most of us, thank goodness, don't have to deal with gig-ohm resistors in the circuit.
Hard to find, too.
Yeah, I mean, gig-ohm resistors. A single-digit picofarads are a problem at audio frequencies with resistors that big. Another question?
Yep. How about what influence would have the capacitive load in your sketch on 2 gigahertz rectification?
You mean like this little guy here, see RFI? It tends to kill it because it's rectification at the input that causes the most problem, because it's like a little crystal radio. Some PN junction, which may not be very good at 2 gigahertz, is good enough to create a rectification, which creates even just millivolts of DC offset. If you've got a gain of 100 in this circuit and you create 2 millivolts of offset, you get a 200 millivolt offset on the outside at the output of the op amp, and then if it's modulate, now you've got that on top of it. The first time I encountered this 30 years, 40 years ago, back at Bell Labs, back in, well, 30 years, 1980-ish. It was the logic noise generated in the board next to it in the shelf would radiate into the fairly large loops in the analog circuits on this board, and what you heard in the op amp, with a voice frequency op amp, it really was carried human voice like in a telephone system, but what you heard in the background was you heard the software cycle running on the next board, rectified into the baseband, and that was amazing. We could, as I mentioned before, you could slide a copper board sheet between them, and it would just make the thing go quiet, even though it was ungrounded, because the local fields of the digital circuit were small enough that all the currents were contained within that shield, and that's for fields that are physically much smaller than the shield. You don't need to ground the shield to get shielding, but of course that was totally impractical. Our system people didn't want to hear of putting copper plates in between the boards, so we had to end up with little capacitors there on the input of the op amp.
Okay.
Question?
This is for everybody. I've been told that placing a capacitor between the inputs of the op amp can cause instability. I've never seen issues. What are your thoughts?
Thoughts? I think the last word cut off there. Are you still there?
Yeah, I just asked what are your thoughts on this?
Oh, okay. Yeah, the word thoughts didn't appear, or maybe the T came through. Well, let me do that. What happens is if you plot the gain and phase of the feedback loop, it does reduce the gain and phase margin. And if you put a big enough capacitor there, and it might not have to be that big, a few hundred picofarads might do it, you can cause things to oscillate in band, and somewhere in the audio band, or up to 1 gig, somewhere in the unity gain bandwidth range. But if you don't want to, say it's an old circuit, I don't know if you guys have ever had the wonderful experience of inheriting someone else's design. And they usually did such a wonderful yes, they did such a wonderful job of explaining what they did, right? So now you don't know anything about this circuit, right? And now you get an RFI problem on an op-amp, and here's my shortcut of doing a simulation or a calculation. You put a capacitor, find out what value gets rid of the RF, and then you keep going, and you find out what value causes an instability. And if you're 1/4 of the instability, and it still fixes the RF, you're probably okay. That's the poor man's quick solution, or the quick solution when the boss is breathing down your neck. Yeah.
Okay, everybody. We have tried.
Anyone have their boss breathe down their neck?
We have about 10 minutes to go. We want to ask a couple more. We have a question that says, we have tried using grounding rings around the op-amp. What is your experience and opinion on those? These are in reference to high impedance nodes.
A grounding ring. Well, one question is it a multi-layer board or a two-layer board? A lot of times op-amps are two-layer boards because they're perceived to be low frequency. So I haven't seen that. And if you had really high impedances, that would help reduce coupling to nearby other things on the board. I've never felt the need to use that, though.
Our attendee said multi-layer, referencing multi-layer.
Okay. So then I'm not sure what a ground ring means. I mean, there are voids in the ground, which we call modes. So I'm not quite sure. What do you mean? I'm not sure.
If the intent is to isolate it, as you say, Doug, then the key there is to have the impedance high enough to isolate it.
Yeah. If you're talking about cutting the planes, that's okay. And sometimes we do that to isolate analog circuits from noise currents flowing through them. It just means you can't bring any path, digital or analog, across that break. You need to go, and I think a lot of people know this, you have to find the common point between the two grounds and go across there so it stays over the common ground. It doesn't, but I think a lot of people know that. Generally, I've never had the need to do anything strange in the layout as long as the analog circuit was compact and included these capacitors that I've shown on the drawing here.
And the component placement of the capacitors are such that the leads are very short. And that's
even though it's a small low-frequency analog circuit, yes, because if they're not short, you'll get the RF in there, and then that causes a baseband problem.
Yeah.
I've never heard anyone advocate long leads for anything.
No, that's bad. I refer to that as bad technical hygiene.
Is what?
Bad technical hygiene.
There you go.
Technical hygiene.
Yeah.
You don't want to get Ebola noise in your circuit.
Okay, we have
There you go.
another question. Many new op-amps are featuring EMI filters. Any comments on the effectiveness of op-amps with internal EMI filters?
Haven't seen any of those, or at least I haven't used any of those. You could imagine putting that little capacitor inside, but then I'd worry about what the capacitor is made out of. If it's part of the silicon structure, it may not act so good for what we're trying to do. Sometimes it's just like on a board where, like for EMC purposes, you can mount little ferrites on the board, or you can put a ferrite on the cable. Often, I found the ferrite on the cable itself actually is more effective than the ones on the board, and that may be the case here too, but I'm not sure. As long as they spec the performance, that's what you really want.
Yeah. Right.
But if they spec the performance, you got to be careful. What's the circuit they're using to spec the performance, and does it bear any relation at all to your circuit?
Right. I do know some manufacturers specify an EMI rejection ratio, but then, yeah, obviously it has a lot of caveats on it because it depends on everything. It depends on the frequency range, the speed, all that stuff.
Yeah. What I would do if I were going to select a part, I would build a board with the ground plane as the second layer, or the bottom layer. It might just be two-layer board. Ground on the one layer, all things over ground. Make my little op-amp circuit. Say like this one here. Here's my input. I would monitor the output with the input and output would come in through SMA connectors, right? And I might even have two inputs, the real one and my RF one that would come in through a resistor also. And then look on the output with the scope both for low frequency AC and DC offset and feed it a controlled amount of RF through the same value resistor you're going to use in your circuit. And this is all nice on it looks like an RF circuit on a ground plane, over a ground plane. It looks like you build a little microwave amplifier, so that's what this thing's going to look like. And that's the only way I know you could actually tell for sure that it's going to work in your circuit with the given RF excitation.
Okay, guys, we only have 5 minutes left, so we're just going to ask one more question. Layout or traces affects the susceptibility of the circuit. Aside from adding capacitors as mentioned, what other solutions do you recommend?
Short.
Yeah.
Short connections.
Yeah.
If you mount the thing over a ground plane, a multi-layer board, then that's sort of good because it helps to cut down the loops for RF purposes. You just have to make sure that you've accounted for any capacitance to the ground plane that's affecting the operation of the circuit.
Right. The same EMI protection rules apply to op amps as apply to any other circuit, I think. If, as Doug says, if there's a clean ground plane, as low impedance path for the noise currents to flow to, then that addresses most of the problem. And whatever options in routing you have, keep the leads short. And if there are decoupling devices on there, and again, we can't repeat that enough, the proximity of those to the pin that they're decoupling has to be very tight, or as tight as possible, and the leads as short as possible. That's key.
Sometimes you can, if you're worried about a specific excitation like a cell phone, you could build a small coaxial dipole, and if I'm an email, I'll put a link to how to get that. You could excite it from a signal generator to simulate a cell phone and hold it near your circuit layout to see what happens, to see what the effect of someone holding a cell phone on top of your product. A lot of products have plastic boxes today, and you might just put your cell phone right on top of the thing. You can simulate that by taking a cell phone-like antenna, like a little coaxial dipole, feed it with 600 milliwatts at 1850 or something, and I think each side of the dipole would be exactly 3 centimeters for that frequency. It turns out to be exactly 3.0 centimeters. So you have a 6 centimeter little dipole. And you can figure that you can get that effect. If you're going to build a dipole into the coax, you need a balun at the end of the coax, a couple of ferrites or something, to prevent the shield of the coax being a third element.
Okay, we have a couple more seconds. Does anybody have any last thoughts before we go back, before we go offline?
It's almost lunchtime.
Lunching and learning.
There you go. That's what we all do.
Like we talked about here, as Doug has reiterated several times here as we talked, the bottom line is just good EMC practice, and that's keep a clean ground plane on your circuit as best you can, as much control over it as you do have. Keep your routing such that the signal leads are short, and the component placement is compact. And if you do have decoupling devices, keep the leads short on those. Well, that's generic advice, but it applies equally to op amps as it does other circuits.
Basically, you have good EMC practice, but apply it to analog circuits that you wouldn't normally think of having to do it to.
Right.
And I liked what you said about treating everything like it's a microwave circuit. I think always keeping the grounds near the signal so that the return is right near the signal is important as well. So same idea, but yep, I all agree with that.
Great. We'd like to thank all of our panelists and our moderator. We received a lot of great questions that we're going to send to everybody, and hopefully we can get these addressed in the future. If you have any more questions or comments, please email us at info@emclive2014.com.
Belinda,
yes.
If you make our email addresses available to them, or just send us the questions and who it came from, I'll try to answer them. It may take a while.
Yes, we will. We have questions from everybody, including ones we haven't gotten to, and we will send them to all of you so they can be addressed.
If they got a critical question, just have them call one of us if they have something that's got a problem today.
Of course. Thank you, everybody. We really enjoyed the roundtable, and we will talk to everybody in the future. If you have any more questions, send us an email, and thank you for attending.
Thank you.
Thank you.